everyone, welcome back to the channel. So today in this video lecture we're going to be solving this problem round trip 2, which is a problem taken from CSES problem set. So this problem is basically a cycle detection problem. So we have already learned about how to detect a cycle in a directed graph. So before moving to this problem, I recommend you to watch that video in the same topological sorting playlist. After that, you will be able to understand this problem better. So let's read the problem statement. So Byteland has n cities and m flight connections. Your task is to design a round trip that begins in a city, goes through one or more other cities, and finally returns to the starting city. Every intermediate city on the route has to be distinct. So basically, Byteland country has some n cities and there are m flight connections. Okay, your task is to design a route. We need to design a route that begins at one of those cities, goes through some of other cities, and comes back to the city where we started. And all the cities, the intermediate cities which we visited, must be distinct. That's what we have to do. Basically, we just want to print the cycle in the given directed graph. That's all. So the first input line will have two integers n and m, representing the number of flights and the flight connections. Okay. Now the cities are numbered from 1 to n. Fine. Basically n nodes m and m edges, and the nodes are numbered from 1 to n. Then we'll have m lines, which describes the flights or the directed edges, where each line has two integers a and b. That means there is a flight connection from city A to city B. Means there is a directed edge from city A towards city B. All connections are one-way flights from a city to another city. Means all the edges are directed edges. So we just have to print the size of the cycle, that is k, and the nodes, the space separated integers in the next line, representing the nodes which are there in the cycle in the order in which they are present in the same cycle which we have detected. If there is no such cycle, if there is no such route, then print impossible. Fine. So simple cycle detection problem will be, let's better understand the problem statement. So let's take this example. We have 4 nodes or 4 cities in the Byteland. So they are numbered from 1 to 4. There are 1, 2, 3, 4, 5 flight connections, okay, among these cities. Now we want to find if there is a cycle or not. We can see that there is a cycle. If we start from node number 1, we can go to node number 3, then we will go to node number 2, then finally we come back to node number 1. So there is a cycle 1, 3, 2, 1. So for this graph, the answer, one of the answers can be 3, or let's say 4, 1, 3, 2, 1. That is the answer. In this format, we have to print our answer. Fine. So if there are multiple cycles, means there are multiple answers to the same problem, we can print any of them. All of them will be valid answers. So let's see how we can solve that problem. This is just an extension to the problem which we have already learned, that is how to detect a cycle in the undirected graph. This is just the application of the same concept. Let's see how to do that. Now, so in that problem we just found if there is a cycle or not, but in this problem we have to actually retrieve the cycle which we have found. That is the only extension we have in this problem. So let's see what we do here. What we're going to do is we'll simply use the same logic, that is iterate over every node, start from node number 1. So we'll start from all of the unvisited nodes. They're numbered from 1 to 4. Start from the first node, check if there is a cycle starting from node number 1. So how would I check that? Take a visited array, perform the depth first search from every node. So first time we'll perform depth first search from node number 1. So let's take a function dfs. So this is a recursive function. Let's take a function dfs which takes in the node and this function is going to check if there is a cycle or not. Okay, if the cycle starts at this node or not, that's what this function is going to check. So let's see the call stack. There will be a call stack because we are calling a recursive function. Depth first search is a recursive function, so we'll have a call stack. As usual, for detecting a cycle, we'll have two things. First, we have to keep track of the parent of the current node or a visited array so that we do not visit the same node again. So we can keep a visited array. Let's see, we have a visited array. Then we'll have recursion stack. Okay, so let's see how we proceed. Okay, so we'll start our DFS from node number 1. We're gonna check if there is a cycle. So we first visit node number 1 and we also put this node into the recursion stack, recursive stack means so this basically this array we use to detect the cycle, as we did in the previous video where we checked if there is a cycle in the directed graph or not. So that's why we're using this array, so that we want to check the back edge, that is this edge. For instance, in this case we move from 1 to 3, then from 3 to 2, finally from 2 to 1. So this is the back edge because 2 is pointing to one of its ancestors. So to detect that back edge, we use this extra array, that is recursion stack array. This basically store all of those nodes which are there in the call stack. Okay, so initially in the call stack we have node number 1. So basically the function call associated with node number 1, that's what I'm saying. Now from node number 1 we'll visit node number 3. So this is visited, this is visited. Now node number 3 is visited, so we mark it as visited, we put it. Then we'll visit node number 2, so we put it here. Then from node number 2 we can see that we encounter this node, that is node number 1, which is already there in the recursion stack. So here in the call stack we'll have 3, we'll have 2. Now here I can see that we visit node number 1 again, and here I observe that it is already there in the recursive stack. So it is there in the recursive stack here. That means we are encountering a back edge. Fine. So if there is a back edge, what we're going to do is, means there is a cycle, the cycle ends at this node, it started at this node. We'll simply store all of the nodes which were there in the way, and all of the nodes are present in the call stack. We have the associated calls in the call stack for those nodes. You can see we visited 1, so we visited 1. We will move back to node number 2, so we store node number 2. Then we'll move back to node number 3, we'll store node number 3. We also removing these nodes from the call stack. Then we'll move back to node number 1, we'll push 1, and this is my cycle. That's what I'm gonna print. That's all we have to do. Fine, so you got it. So since this is just the call stack, I want the actual nodes which are there in the cycle. For that I will use a extra stack. I will use a actual stack here in the array. So let's use a stack and then dry run the algorithm which I am trying to explain here. So we take a stack, let's call it st. So stack st. Now I visit node number 1, I push it into this actual stack. So we started DFS from node number 1, and the function call corresponding to node number 1 would be there in the call stack, and I mark node number 1 as visited, and also in this rec stack array, because remember this array stores all the entries of the nodes for which the function calls are there in the call stack. Also I will push this node into the actual stack which I am using, because this stack will be used to retrieve the actual cycle that we get. Now from node number 1 I will traverse node number 3, so the function call corresponding to node number 3 will be stored in the call stack, and I mark it node number 3 as visited, and I mark its entry in this array because it is there in the call stack. I also push it into the stack. Then from node number 3 I will traverse node number 4, let's say. So I put it over here, the function call corresponding to node number 4, I mark it as visited. Here I mark its entry, and I also push it into this stack. Now I can see that from node number 4 there is no outgoing edge. So I move back to node number 3. I remove this entry from this stack. I remove this entry from this stack, from this array rec stack. I also remove the entry from the call stack because the function call corresponding to node number 4 has been resolved, and we are removing it. Now then we traverse node number 2, so I mark it as visited. I put the function call corresponding to node number 2 in this call stack. I also push node number 2 in the call stack into this actual stack, and also I mark its entry here in this array. Now from node number 2 I encounter node number 1, but then I check that it is already there in this stack. We already have node number 1 in the stack. That means the function call corresponding to node number 1 is present in the call stack, means we are revisiting it in the same path. So the path must have started somewhere. We may have encountered node number 1 along the path. Now I am again revisiting the same node in the same path, because that's why I have the entry, I have the function call entry here in the call stack, which I checked using this array. That means there is a back edge. This node number 2 is pointing to one of its ancestor nodes, for which I have already called this DFS function. Fine. That means there is a cycle, so I push this node here in the stack as well. Okay, so I push this node here in the stack. Now when I find this thing, I will simply traverse over the stack. I will traverse over this stack, and I will keep popping out element and pushing it into a extra auxiliary array, which is used to store the cycle. So I will use a extra auxiliary array, let's call it cycle, and in that cycle I will store all the elements which are there in the stack. So first I will pop node number 1, I will store it there. Then I will pop node number 2, I will store it there. I'll pop node number 3, I'll store it there. So these are popped. Then I'll pop node number 1 again, and I'll store it there. So all of the nodes are there in the stack, and this basically represents the reverse of the cycle that we have, because the cycle is 1 3 2 1. I'm getting 1 2 3 1, so I have to reverse this array. So I will reverse this array, and after reversing I will get 1 3 2 1, which is the actual cycle we have. So I will simply print the size of this array, which is 4. After that I will print this array itself. So that's the procedure. That's all we have to do. A little modification: if you already know how to detect a cycle, then you would be easily able to figure out this solution. So let's jump to the code implementation. Okay, so let's implement the solution. So here we have our main function. We can see that the input that we take in the problem statement is the very first line will be two integers n and m. Then we'll take in the actual adjacency list. So I'll iterate over all the edges. We have m flight connections, where we have two integers a and b for each flight connection. That means there is a flight from a to b. So I create an edge from a to b. It's a directed edge. After that, I will call a function which will return me the cycle. Let's call it a round trip function. We'll see how this function work. So this function takes in the number of nodes, the adjacency list. It will give me the cycle that we have. I will check if we have an empty cycle. So if its size is 0, means that there is no cycle, then I will print impossible. And I will return right from here. I will terminate my program right from here. Otherwise I will print the cycle, I will print the size of the cycle. Then the cycle itself. Okay, so in this fashion we'll have our cycle printed. Let's see the definition of this round trip function. So it basically detects if there is a cycle or not. If there is a cycle, then it returns that cycle. So it takes n nodes and the vector itself. So let's declare arrays. The first array would be visited array of n plus 1 nodes. The second array would be the array which will be used to keep track of the nodes which are there in the call stack. Then we'll have our stack. Fine. Now here I will iterate over all the nodes starting from node number 1 till node number n. If any node is unvisited, if I find a node unvisited, that means there can be a cycle starting from this node. So then I will create another function is cycle, which will be used to check if there is a cycle. I will pass in the node, the starting node where we want to find if there is a cycle or not, the visited array, the recursion array, and the stack, and finally will pass the adjacency list. So if there is a cycle, that means we have found a cycle here. That means I will extract the array, I will extract the cycle from here. So I will call a function, I will create a function extract which takes in this stack and it simply extract the cycle which is present in this stack. Okay, that's all. And this extract function returns me the cycle in the vector. Finally, if I do not find any cycle, then I will return an empty array from the end of this function. So let's create this function is cycle. So this is a boolean function is cycle which takes in the node, the visited array, the stack array, the stack itself, and the adjacency list. Now mark the current node as visited and the recstack array to be visited. Also push this node into the stack because I'm considering it as the part of the cycle. Now iterate over its neighbor nodes. So if any neighbor node is unvisited, if it is unvisited, that means this can be the part of the cycle. So if it can be the part of the cycle, then check if it is. If it is node, pass in this neighbor node, the visited array, recursion stack array, set, and the adjacency list, and return true if there is a cycle. Otherwise we'll check if there is a recursion stack array for the neighbor. If we have otherwise if we have already visited this node, if the neighbor node is already visited, that means we have a back edge. So this is the case of back edge. Here we are including it into the cycle, include it into the cycle, and here we detect a back edge. So if we are detecting a back edge, means there is a cycle, so we return true. Fine. Otherwise I'm gonna pop this node out from the call stack. So I mark it as unvisited here. Also I pop it out from the stack as well, and I will return false from here because there is no cycle which starts from this node. Okay, fine. Now in this fashion we'll check if there is a cycle or not, and we'll have our stack prepared. Now Then we'll call out the stack. Let's create the extract function. So extract function basically extract the actual cycle from the stack. So it takes in the stack as input. Okay, so let's initialize a node with the top element of the stack. Since this is the last element which we have found, so let's declare a cycle array. We push this node into the cycle array, so we push this node into it because this is the part of the cycle, and we pop this node from the stack. Now till the stack is not empty, keep popping out elements and pushing it into the cycle. So cycle dot push back, keep pushing these elements into this cycle array. If the element that we have found here, that is the current element st dot top, so we'll first if the element that we have found here, that is st dot top, if it is same as the node where we started, that means we have a cycle and we break right here. Otherwise we keep popping the elements. So finally we'll have our cycle prepared, cycle array prepared, and will return from the end of this function. So that's all. Let's run it. Let's take this test case from the problem statement itself. There's a problem, cycle dot pushback st dot pop. Okay, it's st dot top, not pop. Okay, okay, 231. So since there's a back edge, means here we can see that we have found this neighbor again, so we have to push this into the stack, because that's how we will detect a cycle while we are retrieving it. So here we have our, and now we have to, so here we forgot to reverse it. We first have to reverse this cycle because we store the cycle in reverse order when we use stack. Okay, so 1321, which is the cycle corresponding to this test case. I am okay, so 1321. Okay, 1321, yes, it is a cycle. Fine, so this is the right answer. So let's submit it. Let's try to submit this solution. Okay, accepted. So that's all I've got for this video, and this problem can also be solved without using stack data structure. So this is an exercise for you. So try to solve this problem without using the auxiliary stack which we have used. So if you like the video, then hit the like button and make sure to subscribe to the channel and stay connected with me, stay tuned with me. I hope to see you all in my next video.